we're going to build up to how to find the greatest common factor and the least common multiple of two numbers. And you can skip ahead if you just want to get straight to the point, but there are some tools that I want to teach you first so that we can build up to it. The first of which is this divisibility test, right? Sometimes you're not exactly sure what certain numbers are divisible by, and these will give us a little insight into that. So, a number is divisible by 2, or we could say 2 divides a number if the number ends in 0, 2, 4, 6, or 8. That's a dead giveaway. 3, this one's my favorite, right? 3 divides a number, or a number is divisible by 3 if the sum of its digits is divisible by 3. And I'll show you how that works here in a minute. Actually, why don't we just do these as we go through it? So, let's look at 4158, right? Is 4158 divisible by 2? Well, the number ends in an 8, so yes. If a number ends in 0, 2, 4, 6, or 8, it is divisible by 2. Now, here's what I mean by the 3 situation, right? We said that 3 divides a number if the sum of its digits is divisible by 3. So what do I mean by that? I mean, we're going to take the number 4,158, and we're going to add up the digits. That is 4 plus 1 plus 5 plus 8. Right? 4 plus 1 is 5, plus 5 is 10, plus 8 is 18, right? And 18 is 18 divisible by 3. Yes, it is. Which means that 4,158 is divisible by 3. So that's how a divisibility check for 3 works. How about 5? 5 divides a number if it ends in a 0 or a 5. Now, does this number in question end in a 0 or a 5? No, it doesn't, so it is not divisible by 5, right? That one is not divisible by 5. How about 6? How can you tell if a number is divisible by 6? Well, 6 divides a number, or a number is divisible by 6, if it is divisible by 2 and 3. So if it's already satisfied 2 and 3, 6 will work. And we have, right? We did satisfy 2, we did satisfy 3, which means this number, the number in question, 4,158, is divisible by 6. And then lastly, how do you know if a number is divisible by 10 just by looking at it? If it ends in a 0. If a number ends in a 0, it is divisible by 10. So 4,158 does not end in a 0. So those are the ways you can figure out if a number is divisible by 2, 3, 5, 6, or 10. So we're also going to do this with 105, 3,740, and 8,580. So if you want to pause the video and try these out, you're more than welcome to. I'm going to go ahead and do them now. So starting with 105. 105 does not end in an even number, so it is not divisible by 2. Let's add up the digits. 1 plus 0 plus 5, that is 6. 6 is divisible by 3, therefore 105 is divisible by 3, right? So that's a check mark there. 105 ends in 5, so it's divisible by 5. Now, 105, it was not divisible by 2, so it's not going to be divisible by 6. Now, yes, it was divisible by 3, but it has to be divisible by 2 and 3 in order to be divisible by 6. And then it doesn't end in a 0, so it is not divisible by 10. All right, how about this 3,740? Well, it ends in a 0, so it's divisible by 2. Let's add up. What's 3 plus 7 plus 4 plus 0? That is 14. 14 is not divisible by 3, so 3,740 is not divisible by 3. It ends in a 0, which means it's divisible by 5. Now, it was divisible by 2, but it's not divisible by 3, so it's not going to be divisible by 6. And it ends in a 0, so it is divisible by 10. So far that's what we have. All right, last one. We have 8,580 ends in a 0. I'm going to speed it up a little bit. It ends in a 0, so it's divisible by 2, 5, and 10, right? We can tell right away. Let's add up the individual digits. 8 plus 5 plus 8 plus 0, that is 21. And 21 is divisible by 3, so this number is divisible by 3. And since 2 and 3 both divide 8580, so will 6. So this last number was divisible by all 5, right? So there you go. Those are the solutions to those. That's just sometimes you may not be able to tell if a larger number like 3,740, it may not be as obvious what numbers divide that. So this gives you a little insight, a little bit of help on how you can break that down. That'll become useful momentarily. All right, let's talk about multiples, right? So here's a formal definition. You don't have to worry about memorizing this, but a number n is a multiple of another number m if n equals a times m for some natural number a. Cool. You may never have to think about that again. But let's just list the first 12 multiples of 3, right? The first 12 multiples of 3. What do I mean? I mean 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. And then 33 and 36, right? Okay, those are the multiples of 3, right? That's what multiples mean. In a very informal explanation, at least remember that multiples of a number will be bigger than the number, right? 3 is the same, but then everything else is bigger. All right, pause the video, and I want you to list out the first 12 multiples of 4. Do it for 4. And that will be 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, and 48. Those are the multiples of 4, right? So that's what multiples are. People get multiples confused with factors. These are multiples. Now let's do factors. Factors will always be smaller. Here's the definition. The numbers a and b are factors of m if a times b equals m. So let's list the factors of the following numbers. So 24 here, you can always start with 1 and 24, right? That's the most obvious pair of factors, 1 and the number itself. How about 2? 24 is 2 times 12. So 2 and 12 are another pair of factors. And yes, these factors will come in pairs, right? 24 is divisible by 3. It's 3 times 8, right? 3 times 8. So those are another pair of factors. And then 24 is divisible by 4, which is, what is that? That's 4 times 7. 4 times 7. No, that didn't feel right. It's 4 times 6. There we go, 4 and 6. So these are the 4 pairs of factors of 24, 8 factors in all. All right, go ahead and pause the video and try to do 28, 13, and 20. List the factors of 28, 13, and 20. For 28, we'll have 1 and 28, right? You'll always have 1 and the number itself. 2 times 14. 28, is it divisible by 3? Nope. 4, how about 4? Yes, 4. Here's your 4 and 7. Those are the factors of 28. Now, 13, obviously, 1 and 13, but there is nothing else, right? The only factors of 13 are 1 and 13. There's a name for that. Will come up shortly. How about 20? 1 and 20, and then 2 and 10, 4 and 5. Those are the factors of 20. Good. So don't get factors and multiples mixed up, right? Multiples are starting with the number and going bigger. Factors are going to involve the number, but smaller, right? 2 and 10 are both less than 20, right? So those are factors of 20. So, all right, good. Let's talk about prime numbers real quick. And we've seen one. That was this, right? What is a prime number? Well, 13 is a prime number. Why? Because the only factors of 13 are 1 and itself. There are no other factors. These are called prime numbers. So this says right here, well, here's the definition. A prime number is a natural number whose only factors are 1 and itself. And then here, list the first 10 prime numbers. So pause and see. Can you list the first 10 prime numbers? First one is 2, and then 3, and then, how about 4? Is 4 a prime number? No, because 4 is divisible by 2. So we're going to skip the 5 as a prime number, 7. Here on out, all the prime numbers are going to be odd. 2 is the only even prime number. So we can skip. We don't need to check 8 because 8 is divisible by 2. How about 9? Well, 9 is divisible by 3. 10 is even. 11. 13. How about 15? No, 15 is divisible by 5. 17. How about 19? Yep, 19. 21. 21 is divisible by 3. How about 23? 23 is prime. 1, 2, 3, 4, 5, 6, 7, 8, 9. We need one more, and that's going to be 29, right? So here are the first 10 prime numbers. It is good to be aware of these numbers. Now, compare this to a composite number, right? A composite number is any natural number which is not prime, so basically everything else. So list any 10 composite numbers. So take a minute, list a few composite numbers. 4 is composite, right? 4 is divisible by 2. 10, any even number other than 2 is going to be composite. So that could be 202, right? That's divisible by 2. What about some odd composite numbers? Well, previously we came across 15. 15 is divisible by 3 and 5. And I said 10, let's just do one more composite number. How about 180? Let's see, 183. That's divisible by 3. How do I know? Because 1 plus 8 plus 3 is 12, and 12 is divisible by 3, so this is a composite number. So here are some composite numbers. Again, it's the opposite of prime. If a number's not prime, it's composite. So there you go. All right, here we go. Let's get into now we're going to actually do some math here. Prime factorization. Use a factor tree to find the prime factorization of the following numbers. So we're going to break apart a number. All of these are going to be composite numbers, and we're going to break them down into their prime pieces, right? Basically the prime numbers that build up these numbers. So you think here, okay, 18. 18 is divisible by what? Well, we could break 18 apart into a 3 and a 6. Right? Now, 3 is a prime number, so that's the end of that branch. However, 6 is a composite number, so we can break that down into 2 and 3. And now 2 and 3 are both prime, so we're done there. So 18 breaks apart into a 2, a 3, and a 3. And we're going to write that, because there's 2 3s, we're going to write that as 3 squared. And that right there, that is the prime factorization of 18. That is 18 broken down into its prime pieces, into the building blocks per se. So that's 2 times 3 squared. All right, good. Why don't you take a minute here, and I want you to do the exact same thing we did with that 18. I want you to do it with 12. Take a minute and see if you can do it with 12. Maybe you broke this down into 3 and 4. Maybe you did 2 and 6. That's fine. And then 4 can be broken down into 2 and 2. And these are the prime numbers. So 12 is broken down into 2 times 2 times 3, which is 2 squared times 3. And that right there, that is the prime factorization of 12. 2 squared times 3. Good. Let's see, how many more do we have on this page? Oh, we got a lot. We got a lot of examples here. So, good. Pick one and try one. I'm going to go through all these quickly right now. All right. So 60, you could break down 60 into 6 and 10. 6 breaks down into 2 and 3, and 10 breaks down into 2 and 5. It looks like we have 2 2s and then a 3 and a 5. So the prime factorization is 2 squared times 3 times 5. That is the prime factorization of 60. How about 56? 56, that is 7 times 8. 8 breaks down into 2 and 4 further breaks down into 2 and 2. So it looks like we have 3 2s and a 7. So the prime factorization of 56 is 2 cubed times 7. How about 80? 80 split up into 8 and 10. 8 can be split up into 2 and 4 into 2 and 2. Let's work down the 10 to a 2 and a 5, right? So it looks like we have 4 2s and a 5. So the prime factorization is 2 to the 4th power times 5. 90. 90 is going to be 9 and 10. 9 can be split into 3 and 3, 10 into 2 and 5. So we have 2 3s, a 2 and a 5. Now, we do like to put these in numerical order, so the 2 will go first. We have 2 3s for a 3 squared times 5, and that is the prime factorization of 90. About 360. 360. I'm going to go with a 36 and 10, right? I'm using that divisibility test. If a number ends in 0, I know it's divisible by 10. So that's the path I'm choosing to go. 10 breaks down into 5 and 2. What about 36? Well, that could be 6 and 6. Now, it may be tempting to stop here and be like, oh, we have two 6s, so we're going to put 6 squared. But 6 is not prime. 6 is still composite. So we need to break down the 6 into 2 and 3 and 2 and 3. Now, careful with the ends of the branches. The ends of the branches here are these 2's. We got 3 2's, 2 3's, and a 5. You should only be ending with prime numbers, right? So the prime factorization of 360 is 2 to the third power times 3 to the second power times 5. And that is the prime factorization of 360. 8 times 9 times 5. All right, good. Then we have 525. Okay, good, exactly. So 525 seems like a large number, but it ends in a 5, so we know it's divisible by 5. Now, does that really help us out? Do we know what 525 is off the top of our heads? Probably not. I don't. I'm going to go and type this into a calculator. And 105, that gives me 105. Okay, well, 105 ends in 5, so that's also going to be divisible by 5. And I believe that's 21. Let's check. Divided by 5, and that gives us, yes, that gives us 21. All right, good. 21, what is 21 divisible by, right? That's divisible by 3 and 7. There we go. So we have 2 5s, a 3, and a 7. So the prime factorization here is 3 times, 5 squared times 7. That's the prime factorization of 525. And then we have 111. So here we go, 111, right? Maybe it's not as obvious what 111 is divisible by. Well, if you add up the digits, 1 plus 1 plus 1, you get 3. 3 is divisible by itself, by 3, so that means 111 is divisible by 3. So 3, and then what is 111 divided by 3? That's going to give us 37, and 37 is actually a prime number. So that problem ends there. The prime factorization is 3 times 37. All right, good. So those are several examples there of how to find prime factorizations, okay? Now, you may be wondering, I thought this lesson was about greatest common factor and least common multiple. Yes, we're right there. I think that's next. Here we go. We need the prime factorizations of numbers to find the GCF and the LCM. So that's why we've been doing this. But here we go. Here is kind of the culmination of the lesson. So we're going to find the greatest common factor. Definition: the greatest common factor of two numbers is the largest number that divides both of them, that divides both numbers. So find the GCF of the following numbers, use their prime factorizations. So we've already done, for the first row here, we've already done the prime factorizations. If you skipped ahead to this part of the video, I'm not going to redo these prime factorizations. The prime factorization of 12 was 2 squared times 3, and the prime factorization of 18 was 2 times 3 squared. Here's how you find the greatest common factor from the prime factorizations. I'm going to use all the prime factors that they have in common. So if we notice, they both have a 2. So we're going to use that. The GCF, we're going to use that too. And they both have a 3. So we're going to use the 3. Well, what about the exponents? You can only use the smallest exponent that appears in either of these prime factorizations. So here, 2, the first 2 has an exponent of 2, but the second 2 technically only has an exponent of 1. So we can only use one of the 2's. The same thing with the 3. Even though this 3 is squared, it has an exponent of 2. This 3 only has an exponent of 1. So we can't use more than 1. So the GCF here is just 2 times 3, which is 6. 6 is the greatest common factor of 12 and 18. In other words, it is the largest number that divides both 12 and 18. I'm going to do it again. We have 60 and 90. So we've already done the prime factorizations of these numbers. The prime factorization of 60 was 2 squared times 3 times 5. The prime factorization of 90 was 2 times 3 squared times 5. So to find the GCF from the prime factorizations, you are going to write down all the prime factors that they have in common. They both have a 2, so we're going to use a 2. They both have a 3, so we're going to use a 3. And they both have a 5, so we're going to use a 5. And then you consider the smallest exponent that is on these prime factors. And if I'm looking at the 2's, the smallest exponent is a 1. If I'm looking at the 3's, the smallest exponent is a 1. And the 5, the smallest exponent is a 1, right? So I can't use anything greater than, technically, a first power on all these is what I'm saying. But that's just 2 times 3 times 5, which is 30. And so 30 is the greatest common factor of 60 and 90, which means that it is the largest number that divides, that goes in to both 60 and 90. All right, let's do this with 56 and 80. We've already worked out the prime factorizations for these. The prime factorization of 56 was 2 to the third power times 7, and the prime factorization of 80 was 2 to the fourth power times 5. All right, so now we're actually going to get a different situation here. But same process is start by writing down all the prime factors that they have in common. They both have a 2, so we're going to use a 2. However, only the 56 produced a 7. The 80 did not produce a 7, so we can't use 7. What about 5? Do they have 5 in common? No, they don't. So we can't use the 7, we can't use the 5, we can only use the 2. Now we're going to look at the exponents. This 2 has an exponent of 3, and this 2 has an exponent of 4. You can only use the smallest one. So we're going to use 2 to the third power. We're going to use 2 to the third power, which is 8. And that is correct. The greatest common factor of 56 and 80 is 8, which means that 8 is the largest number that divides both 56 and 80. All right, good. Pause the video and try one of these. Yes, the numbers get larger faster. They get large. Use your calculator if you need to. Find the prime factorizations and then find the GCF. But I'm going to go through them right now real quick. I'm not going to show how to find these prime factorizations. We've already done that. So the prime factorization of 42 is 2 times 3 times 7. The prime factorization of 126 is 2 times 3 squared times 7. Now, they both have 2's in common, so we can use a 2. They both have 3's, and they both have 7. And the smallest power on any of these is 1. So we're just going to leave it like that. 2 times 3 times 7 is 6 times 7, which is 42. Oh, does 42 go into 126? Yeah. Sometimes the greatest common factor will be one of the numbers themselves. That is possible. And that is because 42 goes into 126. All right, 200. The prime factorization of 200 is 2 cubed times 5 squared. The prime factorization of 1500 is 2 squared times 3 times 5 cubed. All right, let's find the GCF, the greatest common factor. Well, they both have 2's in common. They don't both have 3's, right? There's a 3 here, but there's no 3 over there. So we can't use 3, but they both have 5 in common. All right, good. Now let's look at the exponents. If we're looking at the 2's, one of them has an exponent of 2 and one of them has an exponent of 3. You have to use the smallest one, which is 2. And the same goes for the 5. So the greatest common factor here is 2 squared. Let me rewrite that. 2 squared times 5 squared, which is 4 times 25, and that is 100. 100 is the greatest common factor of these two numbers. 99 and 189. The prime factorization of 99 is 3 squared times 11. The prime factorization of 189 is 3 to the third power times 7. Okay, so what do they have in common? GCF. Well, they both have 3's. And what is the smallest exponent on either of these 3's? 2. They don't have 11 in common and they don't have 7 in common. So the greatest common factor is 3 squared, which is 9. 9 is the largest number that divides both 99 and 189. $220 breaks down into 2 squared times 5 times 11, and 550 breaks down into 2 times 5 squared times 11. So there's some symmetry here in the way I designed this problem. They both have a 2, they both have a 5, and they both have an 11. And that's it. We can't use any higher powers because the smallest power on any of these factors is just 1. 2 times 5 is 10, times 11 is 110. The GCF is 110. $585 breaks down into 3 squared times 5 times 13. And 1755 breaks down into 3 cubed times 5 times 13. Good, they both have a 3 in common, they both have a 5 in common, and they both have 13 in common. All right, let's look at the 3's. The 3's have exponents of 2 and 3. For GCF, you have to use the smaller one, and that is 2. Good, 3 squared times 5 times 13. I'm just typing that into a calculator, times 5 times 13, and that gives me 585. Oh, there you go, 585. So again, we have another example here where one of the numbers themselves was the GCF, right? And that is because 1755 is divisible by 585 already. All right, here we go. Last one on this page. 7546 breaks down into 2 times 7 cubed times 11. And then 11,858 breaks down into 2 times 7 squared times 11 squared. Okay, so what do they have in common? GCF, they have a 2 in common, they have 7 in common, and they have 11 in common. As far as the 2's go, the greatest exponent is, the smallest exponent is 1. As far as the 7's go, the smallest exponent is 2, so we need a 2 here. And then as far as the 11's go, the smallest exponent is 1. So we're only going to keep one of those. And so here we go. We have 2 times 7 squared times 11. And that gives us 1,078. 1,078 is the largest number that divides both of these numbers. And that right there is how you find the GCF using the prime factorization. So prime factorization is useful in computing these. Good, good. All right. Now we're on to the least common multiple. The least common multiple of two numbers is the smallest number that is divisible by both numbers. Find the LCM of the following numbers. Use their prime factorization from the previous page. So I recycled all the same numbers here. So, forgive me for a second here. I'm going to copy and paste all these prime factorizations here. So we have all the prime factorizations, but the strategy here is a little bit different. We're not just going to use the ones that they have in common, and we're not going to use the smallest exponent. Actually, rather the opposite. We're going to use all prime factors, whether or not they have them in common, and then we're going to tag on the greatest exponent for each of those. So it is literally the opposite of what we just did. So least common multiple. We have 2's and we have 3's. It doesn't matter that they have them in common. Now, the highest exponent on any given 2 is a 2, and the highest exponent on any given 3 is also a 2. So we're going to use that. 2 squared times 3 squared, which is 4 times 9, and that is 36. So 36 is the least common multiple of 12 and 18. Right? And realize here, when you're doing least common multiple, more often than not, it's going to be a larger number. When you're doing greatest common factor, more often than not, it's going to be a smaller number, right? That's the difference between a factor and a multiple, informally, of course. But don't mix those up. Don't mix up factors and multiples. So least common multiple of 60 and 90. So how do we do this? You're going to use all of the factors regardless of whether they have it in common or not, right? It just so happens that they have them in common here, but we'll see this differently in the next example. So 2, 3, and 5. And then you're going to use the highest exponent on any of these factors, on any of these prime factors. I see right here, as far as the 2's goes, the highest power is 2. For the 3's, the highest power is also 2. 5 doesn't have an exponent larger than 1. So we're just going to leave that as is. And 2 squared times 3 squared times 5 is going to be 4 times 9 times 5, which is 180. That is the least common multiple of 60 and 90. All right, here's where we really see the difference between this and the greatest common factor. So again, you're going to use all the factors regardless of whether or not they have them in common. So yes, both prime factorizations contain a 2. So we're going to use a 2. We're also going to use the 5. Even though it's not in both of the prime factorizations, it doesn't matter for least common multiple. You're going to use them all, including the 7 as well. Now, what is the highest exponent on the 2's? 4. So we're going to use 2 to the 4th power. This gives us 16 times 35, and I'm going to use a calculator for this one. 16 times 35 is 560. 560 is the least common multiple of 56 and 80, meaning it is the smallest number, least, that is divisible by 56 and 80. That's what that means, right? Okay, good. Go ahead and pause the video if you want and try to find the least common multiple of any of the remaining 6 examples. Here we go. I see a 2, a 3, and a 7. The highest exponent on the 2 is 1, but for the 3 is 2. 7 is 1. So 2 times 3 squared times 7, 2 times 3 squared times 7 is 126. Well, there you go. It is also possible that the least common multiples is one of the numbers themselves, right? And again, 42 divides 126. Therefore, 42 is the greatest common factor and 126 is the least common multiple. In this example, I see a 2, a 3, and a 5. Again, it doesn't matter that they don't have the 3 in common. It just has to appear at least once. Now grab the highest exponent on each of these. For the 2's, the highest exponent is a 3. For the 3, the highest exponent is a 1. For the 5's, the highest exponent is also a 3. So we have 2 to the 3rd power times 3 times 5 to the 3rd power. And this gives us 3,000. So the LCM here, the least common multiple, is 3,000. Between these two prime factorizations, I see a 3, a 7, and an 11. And the highest exponent on the 3 is a 3rd power. So this is 27 times 77, which is 2,079. So 2,079 is the smallest number that is divisible by both 99 and 189. That's what it means to be a least common multiple. Between these two prime factorizations, we have a 2, a 5, and 11. There is a 2 squared and there is a 5 squared, so we need to use those. This is going to give us 2 squared times 5 squared times 11 is 1,100. Between these two prime factorizations, we have a 3, a 5, and a 13. The highest exponent on the 3 is a 3. We need to use that. So that's going to be 3 cubed times 5 times 13, 1,755. Yes, this was our other problem where one of the numbers was the answer, right? Because 585 divides 1755. 585 is the greatest common factor, and 1755 is the least common multiple. Last one, between these two prime factorizations, we have a 2, a 7, and an 11. The highest exponent on the 2 is just 1. On the 7, the highest exponent is 3. On the 11, the highest exponent is 2. And if we multiply this out, we will get 83,006. That is a very specific number, 83,006. And that number is divisible by both of these two numbers right here. So those are the answers to the bottom 6 examples for least common multiple. So the process for finding least common multiple and greatest common factor both require the use of the prime factorization. But the processes specifically then take opposite paths. Thank you for sticking around. We'll see you in the next one.